location of that same thing, but for users whose names start with N through Z. And then you have maybe a single master, but the slaves for reading purposes are distributed and dedicated to only subsets of your users. So what's nice about this model? What's compelling about partitioning? Yeah? OK, perfect. So you have the traffic going to one of the load balancers or one set of your servers. It's relatively straightforward to scale, right? If you have twice as many users, just get a second server. And don't worry about the load on a technical level. Just send half of your users to one server and half to the other. What else is compelling here? Anything? Yeah?
I mean, if one of the load balancers went down, half of your users just don't see it.
OK, so we can spin that as a positive. So if half of your servers goes down or one of your load balancers, at least the other half are not affected. Good spin. OK, and conversely, now half of your users are screwed, right? At least in a more generic model, at least an individual user might have 50% probability of having their account inaccessible. But here, all of Harvard would be offline, or all of MIT. Now, maybe that's frankly fine, because this way, at least, the whole demographic is sort of in the same boat, and you don't have some users working, some users not. But that's a design decision. That's a risk you would need to take on. What else is bad about this model? Yeah? Yeah, perfect. Suppose that Harvard or MIT has a much larger user base, and yet you're dedicating essentially the same amount of hardware to each. You can't, or even sort of taking this more logically, if you don't know in advance what the demographics use cases are going to be, you might have spare cycles on one of the clusters, but you can't take advantage of that unless you start special casing certain users on one server or another. Other downsides? That's enough. All right. But this is actually kind of a theme. So partitioning in and of itself doesn't necessarily feel ideal. But if you think about this more generically, this is kind of like a hash function, right? Where you're hashing on a user's name or on the school name. And Harvard users all go left and MIT users all go right, or vice versa, something like that. So in fact, there exist even more sophisticated databases that are truly clustered databases. And if you like this kind of stuff, check out CS165 or 265, which focuses on information and databases. But what you could do in theory is, if one of the problems here is that when you hash on a user's name, they end up on a given server. But if that server goes down, the data is lost or the data is inaccessible. Well, what if you actually had fancier hash algorithm that when you hash on the user's name or the school name, you actually put the data in multiple places? Not every place, but what's better than putting it in one place? Or at least put it in 2 places or 3 places. And indeed, these clustered file system or clustered databases do exactly that. They'll store multiple copies in different places. And some peer-to-peer networks actually do this as well, so that you have redundancy built into the system. And if in the future you're trying to access that same piece of data and you reach a dead end because one server is offline or something's gone wrong, you can at least check the second output of the hash function, which might be the other cluster, looking for that same data. And so I can't emphasize enough, as silly as it seems to just do things twice sometimes, it's an order of magnitude improvement, right? If you go from 1 to 2, you've doubled the potential capacity that you have, the redundancy that you have. And so this is actually a very prevailing theme when designing file systems and databases, to have this built-in redundancy and the ability to dynamically figure out where your data is. Now, how about this? This is a picture that just simplifies the notion of HA, high availability, which generally means just having 2 sort of peer systems talking back and forth by heartbeats or equivalent to make sure that they can each take over the responsibilities of the other. So who really cares about all of this? Well, so when it comes time to actually making your own website, you're probably not going to have to worry about wiring up physical machines, and you're probably not going to actually have to buy a whole amount of hardware. But increasingly, as things are moving into the cloud, you certainly still need to understand these implications for database replication and redundancy, for actually wiring things up for load balancing and the like. And the upside now is that a lot of these same ideas are increasingly implemented in software via nice web GUIs or via command line tools, instead of actually having to physically wire things. So even the lessons from CS143 and 165 continue to be relevant, just in a more modern context. And let's take this as an example in just a moment. Yeah?
Yeah, if you have multiple masters, what do you do if you write to the same thing on both masters at the same time?
Good question. If you have multiple masters, what do you do if you write to both masters at the same time? Short answer is you don't. That would be a logic error to actually do that. So you would want to set things up in such a way that the data only gets written to one of those servers. And if you're not doing that, it would be a bug most likely in code or in the configuration. And if you did get it, you'd need some way of, after the fact, cleaning it up, removing duplicates somehow. Actually, I can take that back. You might recall from earlier in the semester or some previous course when you can specify indexes on various keys in a database, and you can specify uniqueness constraints and so forth. So in theory, if you did accidentally write a record here and here, but there was some uniqueness constraint, when replication tried to happen, it would not work because it would fail to meet the uniqueness test. So hopefully you would only have one such row in the database. But if the data in the rows is slightly different except for the keys, it's not clear which of them would trump the other. Other questions? So let's take one example here that might relate either to web-based apps or even iOS apps. For instance, I've been, the past 2 or 3 days alone, I've been playing Scramble with friends. And it turns out I really suck at this game. I have lost like all but one of the large N number of games that I've played against this. And even one of our former CS50 students challenged me over the weekend via Facebook. And I was like, OK, that's great. I'll play against Vicky, we'll call her. Vicky is amazing at this game. I had like 200 total points. And Scramble's like Boggle, for those unfamiliar. And if unfamiliar with Boggle, not interesting to describe. Vicky blew me out of the water with like 900 points. And so the next round that we played, I handed the phone to one of our TFs who's much better at Scramble than I am. She still beat him. So this is really just a story to say I'm really into Scramble with words lately. And the relevance academically here is that this is an application that talks to a server. So how do you actually implement a game? And please, if you want to win, challenge me at Scramble with words lately. So Scramble with words. And applications like it talk to a server because you have to maintain a history of scores, and you might have a history of chat records. And even more interesting than something like Scramble with words, which only makes occasional connections to the servers, you've got instant messaging clients on phones. You've got the idea of like iMessage now on iPhones, where you can actually see when the other user is typing. And Facebook chat in a web context certainly maintains some kind of illusion of a persistent connection to a server. So this actually gets hard quickly, whereby if you want to make real-time applications, that kind of suggests that your web application or your native iOS application has to have a constant connection to a server. But at least in the case of web browsers, they're not really designed, at least historically, to have persistent connections to servers. It's HTTP, right? This icon's supposed to spin, and then as soon as the web page comes back, the icon stops spinning, and that's it. It's a stateless protocol. So if you want to implement something like a chat program, whereby you can chat in nearly real time with some other user on the network, or play a game against that other person, which needs you to be in constant contact with one another, well, how can you do this? Well, in the world of HTML, what is the simplest, dumbest, but correct way that you could create the illusion of real-time chat in a browser window, whether mobile or desktop? So I type a message to a friend, I hit send. How do I know when they have written back? Yeah. OK, well, that's even too fancy, right? I could just force the user to reload once in a while, or I could do a meta refresh tag, sort of 1990s style, and just reload the whole page. And that's, in fact, how a lot of chat rooms were implemented historically, whereby you might at least have an iframe in there, so you would only reload part of the page, but you just reload it from time to time. But this is not a very nice UI, right? The thing will flash slightly. The scroll bar might get into the wrong position as the content gets long. It's not a very elegant solution. So there is Ajax, where at least every few seconds you could replace a subset of the page's content a little more seamlessly. But there, too, you're going to have a delay. Maybe it's a second. Maybe you're going to refresh every 5 seconds. And it's kind of a crappy chat client if you have to wait at least 5 seconds just to see what the other person says. It's not really real time. But what's the downside of just throttling things up to just checking the server every second? What's that? So something will break, right? So there's only a finite number of connections per second that a typical server can handle. And the problem with the constant connections and reconnections is you're just wasting so many bits and so much time. Besides, if you take 143, you'll talk about TCP and the three-way handshake where 3 messages have to be exchanged just for a TCP connection to get established. Then you have to send these fairly verbose HTTP headers across the wire just to say something like hi. Then the response has to come back from the server, which is similarly bloated. There's a huge amount of overhead involved in using TCP/IP, and you're doing this sometimes literally to send HI. There's a huge number of bytes that are wasted. So that's not the best use. Ideal would be to incur that expense once, send maybe an expensive message or this 3-way handshake once, but then maintain a constant connection to the server. But browsers have not historically done this. So there's a few workarounds that people have come up with. So has anyone used or know what long polling is? Yeah, Carl.